Happy New Year everyone, welcome back to the channel and to the third episode of Research Papers Summary, where I summarize key highlights and ideas from different AI related research papers. Today I'll be covering an ICLR 2020 workshop paper on name entity recognition, specifically name entity recognition in a low resource setting environment. Now the paper studies the performance of NER for two low resource languages, Hausa and Yoruba. I hope I'm pronouncing those correctly, as those two languages are the second and third most spoken languages in Africa. The paper essentially wants to assess whether different embeddings and distance supervision methods can help increase the performance of NER models. I hope you will find this video useful. As always, any feedbacks are welcome. Let's get to it. If you're new here, my name is Ryan. I'm a first year PhD student based in London, and on this channel we explore and share actionable insights on different topics in AI research, entrepreneurship and life design, encouraging us to take more actions and live a happier and more intentional life. If these topics sound interesting to you, consider subscribing. NER is a classification task that aims to identify words that refers to entities. Entities here can be person, organization, location, or dates. The popularity of neural models and the lack of label training data for certain languages means that we have to rely on distant and weak supervision to semi-automatically create label datasets. With distant supervision and automatic annotations, the paper also explored different noise handling methods to alleviate the noisy errors. Now this paper aims to answer 3 questions which I hope by the end of watching this video you'll be able to answer to. Firstly, how do NER models perform in the two low resource languages? Secondly, are distance supervision that relies on external information good for low resource settings? And thirdly, how does simple and contextualized word embeddings trade off in model size and performance? Now this video will be split into 2 main sections. Firstly, I will cover the methodology of the paper, which I will talk about the datasets, the distance supervision, the different noise handling techniques, and the models. Secondly, I will share the key results presented in the paper, which I hope you'll be able to use to answer those 3 questions. Now let's talk about the methodology of the paper. In terms of datasets, we have 2 datasets here, one for the Hausa language and the other one for the Yoruba language. Now the Hausa dataset here consists of 10,000 training instances and 1,000 test instances. Unfortunately, the paper said that the Hausa dataset wasn't publicly available at the time of writing the paper, and so they couldn't run as many experiments as they would like to. The Yoruba dataset, on the other hand, has 1,101 sentences, which was split into 65, 10, 25% train-val test split. Now the Yoruba dataset only has 5 different types of entities: person, location, organization, date, and others. The author also decided to use the Yoruba-specific fast text word embeddings because it gives a better word similarity scores. Now let's talk about distance supervision methods. In this paper, they explore 2 methods of distance supervision. Firstly, automatic annotation rules. Secondly, matching a list of entities from an external knowledge source. Now in terms of automatic annotation rules, these are rules that are usually derived from domain experts to mass label the training instances. It works best for entities with specific patterns. For example, in a Yoruba dataset, a minimum name length of 2 was set for location, person, and organization, except Nigerian names. For the dates entities, there's a native Yoruba speaker that come up with an annotation rules using 11 date keywords. In terms of matching a list of entities from an external knowledge source, we can obtain these entities lists from dictionaries or knowledge bases such as Freebase or Wikidata. The point here is that we will compare words found in unlabeled text and compare them with the entities from this list. If there is a match, that unlabeled text is assigned that corresponding entity. For the Hausa dataset, the paper only focuses on the person entities list, since they only have limited access to the data. For the Yoruba datasets, we have the entity lists of person, location, and organization from the Wikidata in both English and Yoruba. The paper also extracted a list of person names from different external sources, as well as populating a list of popular Hausa and Yoruba people from Wikipedia. For Yoruba, we evaluated 4 different settings with different amounts of clean data, from 1,000 to full datasets. Now let's talk about noise handling techniques. Now as you can imagine, the labels generated with distance supervision is very noisy. And training with lots of noisy labels might be proven to be more harmful than training with a small set of clean data. And that's why in this paper they explore different noise handling techniques to alleviate some of the noisy errors. The paper experimented with 3 different techniques. Firstly, it uses EM expectation maximization algorithm to estimate a noisy channel where it treats all the data as noisy and does not separate between clean and noisy data. The second technique leveraged a small set of gold standard labels, which is often available even in the low resource settings, to help train the main model and reduce noise. This approach models the relationship between clean and noisy data using a confusion matrix. And the third technique uses a neural network to reduce noise. Now the neural network takes into account the features when it comes to reducing the noise level. And so with more data, it might be able to model more complex noise processes. Now the last part of the methodology section will be about models. Here the paper experimented with two types of models, the bidirectional LSTM and the BERT model. For the bidirectional LSTM, the paper uses both the confusion matrix and the cleaning methods to reduce noisy labels. They repeated the bidirectional LSTM experiment 20 times and reported the average F1 score and standard errors. Now the BERT model was trained by fine-tuning the pre-trained BERT embeddings using the NER data with an additional untrained CRF classifier. The evaluation results was obtained after 5 rounds of experiment, reporting the F1 score and the standard error. Let's now move on to the results section. Now here's a reminder of the 3 questions that I posed at the beginning of this video. To answer the first 2 questions, let's look at the following results. In this figure, Table 1A showcased the results for Hausa. Training data that has 50% clean and 15% distance supervised data performs 15 F1 score point below the 100% clean dataset. The noise channel method was able to close this gap. Table 1B showcased the distance supervision on Yoruba. The quality of the automatically annotated labels differs between classes. Location performs better than person and organization names, maybe because locations are less diverse. With simple date rules, we achieved 48% F1 score, showcasing the importance of domain expertise in data annotations. Overall, a good performance can be achieved using distance supervision. To answer the last question, let's look at the next results. The overall results for Yoruba is in figure 1. For bidirectional LSTM, adding distantly supervised labels always helps. In low resource settings, with 1K and 2K data, it more than doubles the performance. Noise handling also improves results slightly, with the confusion matrix method almost always gives better results. Lastly, training on 5K label data with distance supervised data and noise handling can yield performance close to using 17,000 manually labeled tokens. Now BERT has 110 million parameters, in comparison to 1.5 million parameters in bidirectional LSTM. There's a clear trade-off between size and performance. BERT was able to obtain better results consistently across different training sizes. The F1 score at 1000 settings is 50% of the F1 score at full dataset. For the 1000 and 2000 settings, the distance supervision improves performance slightly. The model reaches peak performance with only clean data. With additional distance supervised data, the performance falls, suggesting that BERT model overfits too much on the noise in the distance supervision. And that's it for today. If you like this video, be sure to subscribe, as I'll be covering more research paper in future videos. Feel free to check out episode 1 and 2 of the series where I cover a survey paper on knowledge graph and the first translation model TransE. Thank you guys for watching. I'll see you guys around next time.